to episode 37 of Math1050 College Algebra. I'm Dennis Allison. Today we're going to be talking about counting principles. Let's go to our list of objectives. Basically, there are three types of problems that we'll be considering today, and they're all basically related to the very first item, and that is the fundamental counting principle. Here's an example of a question that we could answer with the fundamental counting principle, and that is, in how many ways can you answer a true-false test if you know the number of questions? For example, if there were 10 questions on the test, how many ways could you answer it? Then we'll look at permutations, which is related to the fundamental counting principle. And a question that pertains to that might be, in how many ways can the San Francisco Giants arrange their batting order by position? So we'll talk about that in a moment. And then finally, we'll look at combinations. And the question there is, how many 5-card poker hands are possible using an ordinary deck of cards? Okay, well, let's go to the next graphic and we'll look at sort of an introduction to the fundamental counting principle. Here's sort of an outline of my studio dressing room wardrobe. I have a number of stylish frocks. I have a lumberjack plaid shirt. I have my paisley print. I have my blue on white polka dot shirt. And then, of course, I have this shirt that I'm wearing today that they've provided me. Then I also have a choice of celebrity trousers. I could wear my checkered dungarees or my Greco-Roman loincloth. You remember the day I wore that back, I forget the episode. Or I could wear my black cap and gown. Or I could wear the Clan Allison kilt. Yeah, I really like that one. Of course, I could wear the trousers that I'm wearing today. So the question is, with this assortment of dressing wear, how many, shall we say, ensembles could I put together choosing a frock and a pair of trousers? We'll call the black cap and gown a pair of trousers, although that would be a little much, wouldn't it? But for the sake of argument, we'll include that. Okay, well, if we go back and look at that graphic one more time, I need to point out something. How many frocks do I have a choice of there? Looks like there are 4, yeah. The lumberjack plaid, the paisley print, the polka dot, or, of course, this solid blue shirt. And how many pairs of trousers, sort of an extended idea of trousers, are there?
5.
Looks like there are 5, yeah, okay. So I'm wondering, how many ways can I put those together in one form or another? Well, now let's come to the green board, and we'll look at that. So we have 4, let's see, let me get a different marker. We have 4 choices for frocks, and we had 5 choices for trousers. Now, does anybody want to guess in how many ways you could combine one frock and one pair of trousers? 20 ways. Okay, Jeff, now, it looks like you probably multiplied rather than added, for example. And as a matter of fact, that's what the fundamental counting principle is all about. If you can do the first thing in 4 ways, that if I can choose a frock in 4 ways, and if I can choose a pair of trousers in 5 ways, then I can do one and then the other in that order 20 ways, 4 ways times 5 ways. Now, for example, when I go to my wardrobe closet and I choose a frock, well, there's 1, 2, 3. There are actually 4 choices that I have there. And then with each one of those with each one of those frocks, I have 5 pair of trousers. So I'll put 5 branches coming off of this one. And then there's not enough room to show it, but imagine that I put in 5 here, and 5 here. So that'd be 5 and 5 and 5 and 5, 20. So the quick way to come up with an ensemble where you choose this frock and maybe this pair of trousers, the number of ways you come up with a pairing would be 4 times 5. And that, in a nutshell, is the fundamental counting principle. So let's go to the next graphic and we'll see this spelled out in words. Okay, so the fundamental counting principle says that if 2 events occur in sequence, and the first can occur in m ways and the second in n ways, then the 2 events can occur in succession in m times n ways. Okay, now with that principle behind us, let's look at an example of this. Let's go to the next graphic. In how many ways can you answer a 10-question true-false exam if each question is answered? Okay, well, let's see. let's see, a 10 question test. So imagine that I put down 10 spaces here. That represent our 10 answers. Now, in each space, I can put either true or false. Let's see, let me move that down a little bit for you. I can either put true or false for each answer. And I see that's not showing up. So let me try one with another marker here, true or false. Okay, so if these are my options for each of these answers, then I have two ways I can answer the first question. But you know, I have two ways I can answer the second question, and two ways I can answer the third question, etc., until I get to the very end. Now, if I multiply these together according to the fundamental counting principle, instead of just m times n, it'll be 2 times 2 times 2, etc. This is going to give me a product of 2 to the 10th power. And 2 to the 10th power is a little over 1,000. It's 1,024. So if you were guessing on a true-false exam, there are actually 1,024 ways you can answer it. There's only one way you could guess all the answers correct. So we'll talk about probability in the next episode, but the probability of guessing and getting all the questions correct would be 1 in 1,024. We'll talk about probability some more in the next episode. Okay, I tell you what. Now, what if we change the question, this same question, and say, what if you don't answer every question? What if you leave some blank? Of course, somebody might say, well, that'd be kind of foolish because at least you could guess and try to get the answer right. But if we include the option of leaving the answer blank, then there would be 3 possibilities on each question. And so the answer now for the number of possible ways we could answer the questions would be 3 to the 10th power, which is considerably more than 1,000. Okay, let's go to the next problem. Let's go to the next problem. Okay, in this problem, we have a hamburger chain that offers burgers that are so incredible that in addition to the patty, you have all of these choices. You can take lettuce, you could take tomato, you could have pickles, either sweet or dill. You could have bacon, onion. They offer 3 types of buns. There's the toasted, the sourdough, or the plain. There are 3 choices for dressings. And the question is, how many variations are possible? Now, we're going to assume that you are choosing the hamburger patty. Otherwise, I guess we couldn't call it a hamburger. But you do have choices in everything else. You could either take the lettuce or leave it. You could take the bacon addition or leave it off, etc. So we want to figure out how many variations of a hamburger there are. Okay, so let's see. For lettuce, how many choices do we have for lettuce? I'm thinking either you could take lettuce or not. That'd be 2 choices. So I'll put down a 2. Now going down this column for tomato, you can either take tomato or not. So I'll multiply, by 2 again. For pickles, how many choices do we have for pickles?
3.
3 choices, either sweet or dill or
none.
Or none, right?
Or both.
Someone might, yes, exactly. Someone might say both, but I don't think anyone would take sweet and dill at the same time. So let's don't consider that as a reasonable option, although theoretically it's possible. So we'll say there are 3 options for pickles, either sweet or dill or no pickles at all. Now for bacon, let's see, we should multiply by 2. 3 types of buns, toasted, sourdough, or plain. And let's say you do want a bun. Otherwise, I don't think we could call it a hamburger. It would just be a pile of assorted ingredients. So we'll say multiply by 3 in that case. Choice of 3 dressings. So what number shall I multiply there?
3.
4. 3? 4, yeah, Jeff. Jeff, what are you thinking is the 4th option?
No dressing.
No dressing at all. Some people may not want dressing on their burger. And then you could either take onions or not onions, so that would be 2. So I guess this comes down to multiplying 2 times 2 times 3 times 2 times 3 times 4 times 2. Now, you know, if we simplify this a little bit, this is 2 to the 4th times 3 squared times 4. Now, you know 4 is actually 2 squared, so why don't we just put 2 more 2's in here and call that 2 to the 6th. 2 to the 6th times 3 squared. Does anybody know what 2 to the 6th is right offhand? What's 2 to the 3rd?
8.
8, right. So what's 2 to the 6th?
64.
64, right. It'd just be 8 squared, right. This is 2 to the 3rd times 2 to the 3rd. So we have 64 times 9. And 64 times 9, let's see, that's going to be 36, 576. So we have 576 options on how we could choose a hamburger. You know, you could go to this hamburger place every day for lunch, 7 days a week, for about a year and a half before you'd have to choose the same selection twice. That's why the burgers are just so incredible at this hamburger joint. Okay, let's go to the next problem. How many license plates are possible in Utah if the plate has 3 numbers followed by 3 letters? You know, on passenger cars in Utah, currently you have 3 digits followed by 3 letters. So how many plates are possible if you do that? Well, let's see. What principle do you think we'll use to solve this problem? What principle are we discussing here?
Fundamental counting.
A fundamental counting principle, of course. So I'm thinking that I should write down a series of numbers, and if the license plate contains 3 numbers followed by 3 letters, I guess I need a total of 6 blanks. And so how many choices do we have in the first?
10.
10 choices for the 10 digits, and then 10 choices here, and then 10 choices here. So that's going to be 1,000 choices to fill in the first 3 digits. What would be the smallest 3-digit number you could put in here?
0, 0, 0.
0, 0, 0. And what's the biggest you could have?
999.
999. And how many integers are there, including 0, 0, 0 up to 999?
1,000.
That'd be 1,000, right? And that's 10 times 10 times 10. Okay, now we go to the alphabet, and it looks like we have 26 choices here, 26 choices here, and 26 choices here. Now, you know, actually, on license plates, they might restrict some letters from being used in a license plate. Can you think of a reason why?
There are some letter.
Yeah, like, I'm not sure that they actually use all 26 letters in a license plate. Why is that?
If some are reserved, like, I guess, for special cases.
Well, that could be. I'm not aware of that, but that would seem reasonable.
I know government uses certain combinations of
I'm
letters.
Like
thinking,
Q and O look a lot alike, so it might be.
Q and O look a lot alike, and Q and O look a lot like what else? They look like a
Zeros.
0, don't they? So I think O might be eliminated, whereas Q might be. It seems like I've seen Q on license plates. Also, I'm thinking that I may not be used because I may look like a 1. But we're assuming that they're going to use every possible letter, so I'm going to use 26 times 26 times 26, and we'll leave it up to the state licensing bureau to decide whether they want to eliminate a letter or not. So to find out how many license plates are possible, our answer is going to be 10 to the 3rd times 26 to the 3rd, which is, well, let's just see on our calculator how much that is. So if we can zoom in here, well, we know that 10 to the 3rd is 1,000, so I'll just go ahead and enter that, times 26 raised to the power of 3. And that gives us 17,576,000. You notice there are 3 zeros on the end here, which makes sense because we multiplied by 1,000, which has 3 zeros on the end. So we knew it was going to be some multiple of 1,000. So it's 17,576,000. Let's see, 17,576,000 license plates. Now, you know, there aren't nearly that many people in the state of Utah, but do you think there are that many cars in Utah? Well, it's hard to say, but if you think about families that have several cars, if you think about all the businesses that have maybe a fleet of cars, then it's probably not likely they're going to have this many vehicles that we need all those license plates. But before the state gets even close to using up all those license plate numbers, they'll resort to a different system for numbering the license plates. For example, in many states, what they do is they reverse the letters and the numbers. They put the letters first and then the numbers second, and then you have this many license plates all over again. Let me just ask you a couple questions about this while I have these numbers here on the screen. Let's look at some possibilities for changing license plates in the event that these are about to be used up. Which do you think would provide more new license plates? If I changed a digit into a digit into a letter, or a letter into a digit?
A digit into a letter.
Okay, and why do you think that would create more license plates? Let's see, just to make sure everybody understands the question before Stephen answers that. Suppose your license number were 754 ABC. And so the question is, if we change this digit into a letter, would we get more license plates than if we changed this letter into a digit? Which one would make more license plates? Stephen, what is your choice?
I said change the digit into a letter.
Yeah, okay, would change this into a letter, okay, and what is your reasoning for that?
Because we'd be changing one of those numbers up there into
Okay.
26, so
Yeah.
it would be 10 squared now times 26 to the power of 4 would be the total number. That you
Right, so
could
what we're doing is
have.
we're trading off a smaller factor for a bigger factor, so you're going to get a bigger answer. So you're going to get even more than 17,500,000, whatever it was, something like that. Okay, of course, now if you were to change a letter into a digit, then you'd be changing a 26 into a 10, and you'd actually be decreasing the number of license plates that were possible in that case. Now, you know what a lot of states have done is they've changed individual digits in the letters. So you may have a digit, or rather a letter, followed by 2 digits and then 3 letters. Or you may put a letter in the middle, have a digit on either side, or you may have a letter in the 3rd position. So in other words, there's a number of ways you can make variations of these license plates. Now, another question, what do you think would have a greater effect if we were to do as Stephen just suggested and change the digit into a letter, or as an option, what if we added an extra digit? So this one being the new position. So I now have the 10, the 10, the 10, 26, 26, 26, but I'm going to add an extra digit in front. So now I have a 4-digit number followed by 3 letters. Which do you think here would make more possible license plates?
The top one.
Let's see. Okay, now in the top case, we said that would be, well, it was 10 cubed times 26 cubed. Now it's going to be 10 squared times 26 to the 4th, which is how much? Let's see. Let's go to the calculator and work that one out. Now we have 10 squared times 26 to the 4th. 10 squared's, whoops, let's see, let me clear that. 10 squared's 100, I'll go ahead and write that one down, times 26 raised to the 4th power, which is going to be 45,697,600. Let's say that's going to be around 45,700,000. Okay? So 45,700,000. Now, while I have the calculator up here, let's go ahead and do the other case. What numbers would I enter if I actually added an extra digit in front?
10 to the 4th times 26 to the 3rd.
10 to the 4th times 26 to the 3rd. Okay, now 10 to the 4th is going to be 10,000. Let's just verify that. 10 raised to the 4th power. And then I'm going to multiply that times 26 to the 3rd. And you see now I have 4 zeros on the end of the number because I'm multiplying by 10 to the 4th, or 10,000. And this is going to be 175,760,000. Well, there's no comparison. It looks like if you add the extra digit, you get 10 times as many license plates. But if you change the 10 to a 26, you're going to do a little bit more than double it. You're not going to quite triple it because you've replaced 10 with a number that's not even the triple of 10. So we're going to get many more license plates by adding an extra digit in that case. Okay, Let's go to the next. Let's go to the next graphic. Okay, here's a problem that's more visual, I think. And it says on this first cube with the a and the b's located on it, suppose you want to travel from a to b along the edges of the cube shown to the right. What is the length of the shortest path? Well, let's see. If that's when I say a unit cube, what I mean is that every edge there is 1 unit long, like maybe 1 foot long. So if I go from A to B, then I could travel, say, this way, and then this way. How long would that path be?
3 units.
It'd be 3 units. Now, another possibility is I could go this way, and then I could go straight up, and then I could go across the top, and that's going to be a length of 3 also. And in fact, I think if you even go back behind the cube, you can go, say, back this way, then you can go up, and then you can go over. That would still be 3. So I think every path along here is going to be 3 units long. Now let me ask you a question. In how many ways can I travel from A to B? Well, you know, what this involves is making some sort of decision every time I travel along a unit length. In the beginning, how many options do I have?
2.
3.
3.
3, actually. Yeah, this would include the path going back behind that we let me just kind of draw that in here that we haven't shown in the illustration. So, you know, we could go to the right, we could go up, or we could go back behind. Now, once I get to the next point, either here, or back there, no matter which place I get to, how many choices do I have for my next move?
2.
I have only 2. Yeah, because we're moving toward B. So, for example, if you're at this corner, you can go back or you can go up. If you're up at this corner, you can go to the right or you can go back. And if you're at this hidden corner back here, you can go to the right or you can go up. So when I get to the second stage, I have 2 choices. Now, when I get to the third stage, let's see, actually this would be the end of the second stage. It looks like I have only 1 choice. I'm going to go directly to B. Or if I get to here, I go directly to B. Or if I go to here, I go directly to B. So to sum that up, it looks like in the first position, I have 3 choices. In the second position, I have 2 choices. And in the third position, I have only 1 choice. And if I multiply those together, I get 6. By the way, we have a symbol for this. What do we call 3 times 2 times 1?
3 factorial.
3 factorial, yeah. So we have 3 factorial ways that we can go from A to B, and that ends up being a total of 6 choices. Okay, now here's the real problem, and that is, go to the second illustration over here, going from A to C, and the question is to find the number of options for the shortest path from A to C in this second illustration. So in how many ways can I go from A to C if I assume I'm following the shortest path? Now what I mean by that is you don't go over and up and then back down again and then back and then up. In other words, you would just be retracing your step. So you always want to be making progress to get towards C. Anyone have an idea how you could solve this problem? The number of ways you can get from A to C. Stephen.
Well, in the first cube, we're going to want to get to the place that was point B, so there's going to be 6 ways to get to there.
Yeah, let me just write a B in right there. You see, these 2 cubes touch right there at that vertex. So as you leave one cube, you go on to the next cube. So you had 6 ways to go from A to B.
And then there'll be 6 ways again to get from B to C. So
From B to C.
6 times 6 ways.
6 times 6, yeah. So because we know there are 6 ways you can go from A to the 4-corner B and then do the same thing from B going to C, if I can do the first thing 6 ways and I can do the second thing 6 ways, there are 6 times 6 are 36. 6 times 6 are 36 ways that I can travel from A to C along the shortest path. By the way, how long would the shortest path be if these are both unit cubes?
6?
Yes, because you'd travel a distance of 3 on the first cube and then a distance of 3 on the second cube. Okay, well now let's introduce permutations, and let's do this by going to the next graphic. Now, if I take a permutation of objects, what I mean is I'm going to count the number of ways that I can rearrange the objects in some order. So in this graphic, it says that a permutations on a set of members of a set of distinct objects is an ordering of those objects. And I want to count the number of permutations of those n objects. Now, what if I were taking them r at a time? That is, I'm not using all of them, but I'm using some subset of them. The number of permutations on n objects taken r at a time, which is abbreviated as p of nr, can be calculated using this formula right here. Now, let me explain the formula, where it comes from, and we'll also illustrate what we mean by a permutation. Let's go to the green board. Okay, suppose I have 5 objects. Let's say 5 books. Let's say here's a book. This is my math book. I'll put an M on top of it. And then I have a history book. So I'll put an H on top of that. And then let's say we have a psychology book. I'll put a P on top of it for psychology. And then I have one more book. That might be my English book, let's say. I'll put an E on top of that. So this is my set of objects, and I want to count the number of ways that I can arrange them. Well, if I'm going to arrange them, I would consider 4 blanks, and I have 4 ways that I can fill in the first blank with one of those books. And then I have 3 ways left that I can fill in the next blank, because I've already used up one of the books here. And then I have 2 ways I can fill in the next slot. And then once I filled in those 3, there's only 1 book left. There's only 1 way I can fill in the last slot. And this gives me 4 factorial, or 24 ways that I can arrange those 4 books in order. Now, suppose I didn't want to use all the books. Suppose I was only going to pick 3 of the books. In how many ways could I arrange 3 books? Well, let's see. There would be only 3 blanks to fill in. One of these books is not going to be used. How many ways could I choose one of those books to fill in the first space?
4.
4 ways. And in how many ways could I fill in the second space?
3.
3. And then 2. Now there's 1 book left over that I haven't used here. And this gives me 24 once again. So there are still 24 ways that I can arrange 3 books out of 4. Now the way I would describe this is I would say this is the number of permutations on 4 objects taken 3 at a time, because I'm only using 3 books at a time. Okay, one more question. What if I was only going to take 2 of those books? And how many ways could I arrange 2 of those 4 books in order? Well, there are 4 ways that I could fill in the first space, and there are 3 ways I could fill in the second space. The other 2 books are not going to be used. And this gives me 12 ways that I could arrange 2 books out of 4. So I would call this the number of permutations on 4 objects taken 2 at a time. So here's what we have calculated symbolically. If I count the number of permutations on 4 objects taken 4 at a time, we saw that that was 4 factorial, or 24. If I count the number of ways of counting the permutations on 4 objects taken 3 at a time, we saw that was 4 times 3 times 2, and that's also 24. And if I count the number of permutations on 4 objects taken 2 at a time, that was only 4 times 3, and that's equal to 12 in that case. So you see how this notation goes. 4 represents the number of objects I have to choose from, and R, or the 2 in this case, represents the number of objects that are actually being counted. Now, you know, in some textbooks, they abbreviate this first one as P sub 4, where this is the number of objects you have to choose from. This is the number of objects you actually use. And some books then would also write this one as P sub 4. 4 objects taken 3 at a time. And of course, this last one would be P sub 4, 2. Now, you know, one case we didn't consider is what would be P sub 4, 1, or P of the ordered pair 4, 1. In how many ways can you arrange 4 objects when they're taken 1 at a time?
4.
That'd be 4, yeah, because there'd only be 1 blank to fill in. That would be 4 in that case. Now, you know, there's a formula that will compute this, and the formula goes as follows. And this is the formula that you just saw in that graphic a moment ago. And it says that if you want to calculate P of n r, and of course this is assuming that n is greater than or equal to r, and r is greater than or equal to 0, then the formula says what you do is you take n factorial and you divide it by the difference factorial, n minus r factorial. Now you might say, where in the world does that come from? Well, let's just take a look at how this comes about. Suppose that I had n books, not 4, but n books, and suppose I wanted to choose r of them to arrange. In how many ways could I arrange n objects when they're taken r at a time? Well, in this case, I would have to write down r blanks, because those are the r spaces that I'll need to fill in. So I have r spaces. And I have n books to choose from. So that means I could fill in the first slot with one of n books. How many books would be left over for the second slot?
N minus 1.
N minus 1, yep. How many books would be left over for this slot?
N minus 2.
N minus 2, yeah. Now you notice the number that you're subtracting off is not quite the position number. I didn't subtract off 3, I subtracted off 2. So I'm subtracting off 1 less than the position number, and that's because in the very first position I subtracted off 0. So I started subtracting 0, then I subtracted 1, then I subtracted 2. And the next one, of course, would be n minus 3. Now when I get down here to the rth space, if that makes sense, the space number r, then I'll be subtracting not r, I'll be subtracting r minus 1. Or if I distribute that negative sign, that'll be n minus r plus 1. So if I want to calculate in how many ways I can fill in r spaces from n objects, I'll need to multiply those together. So I guess what this tells me is that P of nr should be n times n minus 1 times n minus 2, and that just keeps on going until I get to this last space, n minus the quantity r minus 1. Or if you prefer, n minus r plus 1. So I'll need to multiply those together. Now, you know, that looks like a very messy calculation. I have to multiply those all out. So I tell you what I'm going to do. I'm going to go ahead and fill in all of the remaining numbers so that this goes all the way down to 1. I'm going to take n minus 1, n minus 2, and then when I get to this number, n minus r minus 1, and then the next number that I'll subtract off, you notice these are going up, minus 1, minus 2. So the next number that I would put here would be n minus r. That would be the next number that goes up after r minus 1. And I'll keep going until finally I come to a 1, because these differences are decreasing, and so eventually I'll get to a 1. Now I'll have to divide by any new factors that I've just included. Well, the factors that I have here are the same as the factors that I started with, but these are the new factors. That's n minus r all the way down to 1. Well, you know, this is n minus r factorial that's on the bottom. And what is this on top?
N factorial?
That's n factorial. And look, that's our formula right there. N factorial over n minus r factorial. So what I've done is I've included extra factors so that I get a factorial on top. But that meant I had to divide by those same extra factors. And this is n minus r factorial on the bottom. Hence, we have our formula. Okay, now let's just try our formula in verifying that problem about 4 books taken 4 or 3 or 2 at a time. So let's just verify our formula for those same numbers that we just looked at. Let's see, we had P of 4, 4. Now you remember that was where we had 4 books and we were choosing them 4 at a time. So this would be 4 factorial over the difference factorial. That would be 4 minus 4 factorial. Or 4 factorial over 0 factorial. Or 4 factorial over, let's see, what is 0 factorial?
1.
Yeah, remember, just by definition, we say 0 factorial is 1. And so this gives me 4 factorial, or 24 ways of arranging 4 books taken 4 at a time. If I take P of 4, 3, this would be 4 factorial over the difference factorial. And that's 4 factorial over 1 again, or 4 factorial, which is 24. And you remember that was the answer for 4 books, chosen 3 at a time. Now, how many permutations are there on 4 books taken 2 at a time? Well, that'll be 4 factorial divided by the difference factorial, 2 factorial. And now, rather than multiplying these numbers out individually, I would say let's write 4 times 3 times 2 times 1 over 2 times 1. In other words, we can see that part of this cancels. And there's my 4 times 3, or 12, just like we saw before. If you prefer to multiply out 4 factorial and 2 factorial, you can do 2 factorials too. You can certainly do that, and you'll get the very same answer. Okay, let's go to the next graphic and look at another example. In how many ways can 5 books be arranged on a shelf? Well, in terms of permutations, this would be P of 5, 5. Or, the other way to write it is to call it P sub 5, 5. That's the number of permutations on 5 objects taken 5 at a time. And this will be 5 factorial divided by the difference factorial, 0 factorial, which is 5 factorial. And, we just found out that 4 factorial was 24. And this just has an extra factor in it of 5. This will be 5 times 24, and that's 120. So there are 120 ways of arranging 5 books. Okay, let's go to a different problem. Okay, so in this next problem, we'll see a problem that can be done 2 different ways. In how many ways can a class of 30 students elect a president, a vice president, secretary, and treasurer, assuming that no one student can hold 2 offices? Well, now, one way to work this problem would be to use the fundamental counting principle and to think of there being 4 spaces where we make a choice for president, for vice president, secretary, and treasurer. And there are 30 ways that we can elect a president. And then once that office is filled, there are 29 choices for vice president, 28 choices for secretary, and then 27 choices for treasurer. So if I multiply these numbers together, we will get, well, let's see here. We will get, if we zoom in, 30 times 29 times 28 times 27. So they're going to be 657,720. That's almost 2/3 of a million. Let's write that down here. 657,720. Now, the other way that we could work this problem would be to do it in terms of a permutation. So that would be P of 34. And that would be 30 factorial divided by the difference factorial, 26 factorial. Now, we obviously wouldn't want to write out all of these factors on top and bottom and cancel, but I think you can see that if you cancel 26 factorial out of 30, what will be left on top will be the 30, the 29, the 28, and the 27, where 26 on down have canceled off. And you see that's exactly what I've written up above and multiplied together. So it seems reasonable then that this ratio is going to be the same as that product right here. Now, we've already computed that answer, but let me show you how to find this on a calculator. If I go to my TI-82, the way I'll calculate this is to enter 30, and then I'll go to the Math button, and let me just raise this up so you can see it. There's a button here that says Math. If I push that, and I scroll over to the right, under PRB, that stands for probability, you notice there's, on item number 2, it says NPR. That's the number of permutations on N objects taken R at a time. Now, I'm going to insert that right now after the 30. So if I insert that, I have 30. That's my value for N. And now I'll enter 4 for my value for R. Because you remember there were 30 things taken 4 at a time. And if I push enter, I get 657, 720, exactly. Let's just go back to that screen one more time, and you'll notice that under Math, and if I scroll over to PR, I also have a factorial item here that I can choose. So if you want to compute a factorial, if you go under the Math button, under the menu PRB, you can find your factorial that you could enter at that point. You know, on a lot of calculators, on simpler calculators than a graphing calculator, they'll have NPR and the factorial on the keyboard, and you can actually access it directly on the keyboard. So you might look for that on your calculator if you have that available to you. Okay, so this answer turned out to be 657, 720 by this alternate approach. Okay, we have another permutation problem on the next graphic. In this case, it says 6 friends sit together in one row at a movie. In how many ways can they sit together? Well, in terms of permutations, that would be P of 6 people taken 6 at a time. In how many ways can they be arranged? So when I multiply that out, that would be, let's go to the green screen. That would be P of 6, 6, which is 6 factorial over 0 factorial, or simply 6 factorial. You see, we have 6 ways the first person can be placed in a seat. Then we have 5 ways for the second person, and then 4, and then 3, and then 2, and then 1. So whether you think of it that way or using the formula, we get 6 factorial. And if I'm not mistaken, that turns out to be 720 ways for 6 people to sit in the theater next to one another. Now let's go back to that graphic, and we'll look at another question that's asked. The next question says, in how many ways can they sit together if 2 of them insist on sitting side by side? You know, you've been to the theater with that couple before. Yeah, they have to sit side by side. So anyone have a suggestion on how we could work that? See, we have 6 people at the theater. They're going to sit in a row, but 2 of them want to sit next to each other.
You could treat them as if they're one object, and then the 4 others are a different object.
Yeah.
So there's 5 people sitting in 5.
Yeah, you know, I bet it's going to be something about 5 factorial, because if they have to sit together, we just kind of think of them as one group, as one person. And so we kind of think of this as being 5 people sitting in a row, when really there are 2 next to each other. Okay, now on the green screen, this would say take P of 5, 5. However, there's one other issue we have to take care of. In which order do those 2 sit? Like, if the 2 people are John and Mary, does John sit on the right of Mary, or does Mary sit on the right of John?
So you double it.
We have to double it, exactly. So we're going to have to double this 2 times P of 5, 5. And this gives me 2 times 5 factorial over 0 factorial, which is 2 times, let's see, 5 factorial is 120, and that's 240. Okay, so out of the 720 ways of seating these people, 240 of them have John and Mary sitting next to each other. Okay, but you know what happens? John and Mary have a falling out. Now let's go back to that last graphic. Now, in the last part, it says, what if 2 people refuse to sit side by side? So let's say John and Mary don't want any part of each other now. How many ways can they be seated so that they're not sitting next to each other? Okay, well, if we come back to the green screen, okay, now let's go back to that graphic one more time and look at the last question. What if 2 people refuse to sit side by side? Now, you see, what if John and Mary have had a falling out, and now rather than wanting to sit side by side, they refuse to sit side by side? In how many ways could that happen? Well, if you go to the green screen, it says that altogether there were 720 ways that we could seat the 6 people. In 240 ways, they're sitting side by side. So now let me ask the class, in how many ways are they not sitting side by side?
480.
480, yeah, it'd just be whatever's left over when I subtract those. So if we take 720 and subtract off 240, we have 480 ways in which the 6 people can be seated, and these 2 particular people are not sitting side by side. Yeah. Okay, well, let's go now to the next problem on the next graphic. Okay, in this problem, it says you are given 5 balls, each of a different color, and then we have 2 questions. The first one is one that we've actually worked before, I think, or something very much like it, but the second one is a derivative of that. The first question says, in how many ways can these 5 balls be arranged? Now, if they're all of a different color, then we can distinguish each ball separately. And so there would be 5 objects taken 5 at a time, and this would be P of 5, 5, which is 5 factorial over 0 factorial, or 5 factorial. And that's 120 ways of arranging the balls. Okay, but now, do you think there would be more or fewer possibilities if we change the condition to there being 3 red and 2 yellow? Do you think we'll have more possibilities than 120 or fewer?
Fewer.
There'll be fewer, yeah, because now if 3 are red, if I switch 2 red balls, we wouldn't know the difference. So it would be counted as the same arrangement. For example, if you had red, 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 yellow, yellow, and you switch 2 of the reds, it's still red, 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 yellow, yellow. So we'd have to count that one twice. So what I need to do is to find out within this 120, how many of them would I duplicate if I make 3 of them red, and in how many of these would I duplicate if I have 2 of them yellow? So I think what I'll need to do at this time is to take the total number of permutations, P of 5, 5, and I'll need to divide out all of the ways in which the 3 balls can be rearranged, because any rearrangement of the 3 red balls is going to count as the same arrangement. And let's see, the number of permutations on 3 red balls, taken 3 at a time, is P of 3, 3. Now what this is doing is counting out the number of ways the 3 red balls can be rearranged in their positions, and I want to count that only one time. And in the same way, there are 2 yellows. Now I could switch the 2 yellows and I wouldn't recognize any difference in one of the arrangements. So I'm going to divide out P of 2, 2. And this gives me 5 factorial over 3 factorial times 2 factorial. And this gives me, let's see now, if I cancel one of these out, I'm going to cancel the larger factorial, the 3 factorial. That gives me 5 times 4, and I'm canceling the 3, the 2, and the 1. But I still have to divide by 2 factorial, or 2. And this gives me 10 ways of arranging 3 red balls and 2 yellow balls in some ordering. In fact, 10 is so small, let's see if we can actually write them down. If we just go to the green screen, let's try determining what are the 10 ways I could arrange 3 red and 2 yellow balls. So we have red, 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 yellow, yellow. In fact, that's one of the arrangements of the 5 balls. Now, if I count other arrangements, what I'll do is try moving this yellow one through the red, so there could be a red, a yellow, red, and yellow. That's where I switch the yellow with this red. Now let's move that yellow over one more time. Red, yellow, red, red, yellow. And then let's move it one more time. Yellow, red, 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 and yellow. But you notice if I were to switch these 2 yellows right here, that would still be the same arrangements. That's why I divided by 2 factorial. And if I switch any 2 of the 3 reds right here, that would still be the same arrangement. That's why I divided by 3 factorial. Now, you know what I've done is I've moved this y all the way through. Now let's move this second y all the way through. So I'm going to switch that y right here, and I get red, red, yellow, yellow, red. Okay, so I've switched it with this red. Now let's try switching it with this red. Red, yellow, red, yellow, red. So I switched it here. Now, you know, another possibility is I could switch the yellow with this red, and that would be yellow, red, red, yellow, red. So I've switched it right there. So that's moved the yellow into the second position, actually that'd be the 4th position. Now let's try moving this second yellow into the 3rd position. I could switch it right here, and I would get red, yellow, yellow, red, red. Or I could switch it right here, and that would be yellow, red, yellow. Yellow, red, yellow, red, and red. Now, is there any way I can get the second yellow into the 2nd column? I think the only way to do it would be to switch it right here, and that would be yellow, yellow, red, red, and red. Now, how many orderings do I have here? 2, 4, 6, 8, 10. Those are the 10 orderings of 3 red and 2 yellow that we've actually listed. Now, of course, when the answer is only 10, it's not that difficult to write out all those arrangements. If the answer had been 120, we wouldn't want to approach it this way, but for a small number like this, we can work it out. Okay, let's go to the next graphic, and we'll conclude this by looking at combinations. Now, in this case, a combination of members of a set of distinct objects is a subset of the objects where the ordering is no longer important. And the number of combinations of n objects taken r at a time will abbreviate as C in r, and it's computed by the formula n factorial over r factorial times n minus r factorial. So you notice that the difference here is I have an extra factor in the denominator. r factorial as well as the difference factorial. And you notice we've seen this before. This is the same thing as the binomial coefficient in R that we just discussed recently when we looked at the binomial theorem. Okay, so the difference between combinations and permutations is we're no longer counting order. We're only calculating the number of subsets that we could choose. So let's go to a problem where we could apply this. In how many ways can a class of 30 students select a committee of 3 to represent them? This assumes the order of the selection makes no difference. Now, you know, just a few moments ago, we worked a problem where the class was electing officers. And so, of course, the order in which we choose the people is important because the first person we pick, we were assuming would be the president. The second person would be the vice president. This time, we just want to pick committees of 3. And in how many ways can we choose committees? So what we'll do is compute the number of combinations on 30 objects chosen 3 at a time. So these are the 30 students in the class, we're choosing a committee of 3 people. And according to the formula, this is 30 factorial over 3 factorial times the difference factorial. That'll be 27 factorial. Okay, well, if I cancel off the 27 factorial, I'll have 30 times 29 times 28, and I'll divide it by 3 factorial, or 3 times 2 times 1. Now, you know, I can cancel the 3 with the 30 to give me a 10. That'll be a 10. I'll put the 10 right over here. And I can cancel the 2 with the 28 and get a 14. So this ends up being 10 times 29 times 14. Now, let's compute this on a calculator, and then we'll look for a button that will allow us to compute combinations more quickly. Okay, so we want to multiply 10 times 29 times 14. And we get 4,060. So you remember when we were electing officers, I still have that up here on the screen, we had almost 2/3 of 1,657 ways we could elect 4 officers. Now we're selecting how many committees of 3 people could be chosen. And look how much smaller it is. Of course, we're only choosing 3 people, but it's just over 4,000, or 4,060. Okay, now here's an alternative to solving that problem. Suppose on the same screen here, I'll show this. I'm going to enter 30. And then I'm going to go to my math menu. Let's see if you can pull out just a little bit. I'm going to go to the math button, and I'm going to scroll over to under PRB, probability. And you see on the 3rd line, I have the number of combinations on n objects taken R at a time. Okay, so I'm going to enter that. And we're looking at, whoops, I must have pushed the wrong button. Let me do that one again. I'm going to enter 30. Push the math button, and I'm going to enter number 3. And, okay. So we have 30 objects, and we're choosing these 3 at a time because we're choosing committees of 3. Now, if I enter that, I get 4,060. Yeah, just like we computed before. Okay, now one of the things you may be wondering about is where the extra factor comes from in the denominator in our combinations formula. Well, you know, if you look at the number of permutations on n objects taken R at a time, the formula was n factorial over n minus r factorial. This is where we were choosing R objects out of a total of n objects and counting all of those arrangements. But you see, within those R objects, we have those R objects arranged in different orderings. And if I'm choosing committees, I only want to count those once rather than all of the various rearrangement of those R objects. So when I go to calculate the number of combinations on n objects taken R at a time, I'm going to take the number of permutations and divide it by the number of ways those R objects can be arranged. And the number of ways the R objects can be arranged is R factorial, or another way to write this is P of R. So this ends up being n factorial divided by n minus r factorial divided by r factorial. And that's the same thing if I invert and multiply as n factorial over r factorial times n minus r factorial. And the purpose of this factor is to eliminate all the duplications of the various rearrangements of those R objects, since the ordering makes no difference in combinations. Okay, as our last example, let's look at how many ways that a 5-card poker hand can be dealt when using an ordinary deck of 52 cards. So, you know, in the game of poker, you're dealt 5 cards, and we're wondering in how many ways you could get 5 cards out of a deck of 52 cards. Now, this is clearly a problem of combinations rather than permutations, because we're not looking at the order you receive the cards, just the cards that you receive once they've been dealt out. And this would be the number of combinations on 52 objects taken 5 at a time. Now, if I were to use the formula, that would be 52 factorial divided by 5 factorial times the difference factorial. Now, the difference here is 47, so that'll be 47 factorial. And if I were to cancel off 47 factorial, what would be left in the numerator?
52 times 51 times 50
Right. Times 50 times...
49.
Times 49.
Times 48.
Times 48, and that would be divided by 5 times 4 times 3 times 2 times 1. Now, of course, we could actually multiply that out on our calculator, but instead, let's go to our menu and choose combinations from our math key. So let's see, I'm going to enter 52, and then under the math key, I'll scroll over to probability, and I'll select number 3 and enter that. Whoops, let's see, why is there an error? Okay, and that's going to be chosen 5 at a time. And when I enter that, I get 2,598,960. In other words, this is about 2.6 million, roughly 2.6 million. So let's just put that down here as our answer, approximately 2.6 million ways that you can receive your hand in poker. Well, thank you very much. We'll see you next time for episode 38.